Last video we looked at representative elements, and representative elements always have the same cation charge. So if you have aluminum, that's a representative element, it lives in the p block, it always has a +3 charge. You don't have to do anything special with that one. If you have magnesium, it lives in group 2, it always has a +2 charge. You don't have to do anything special with that one when you're naming the cation. These that we're going to look at today have transition metals. Transition metals have varying numbers of valence electrons. So because they have varying numbers of valence electrons, as we learned earlier, you're going to use a Roman numeral that's going to tell the charge of the cation. Your anions all live in the p block, so you don't have to worry about Roman numerals with those. This is just elements that live in the transition metals. So you only have to worry about these with your cations. So when we're looking at the nomenclature here, you're going to put your cation. After you put your cation, then you're going to put a Roman numeral in the middle, and then after your Roman numeral, you're going to write your anion. Otherwise, it's identical to what we did before. If you have the name, you're going to swap and drop to write the formula. If you have the formula, you're going to have to do a little bit of investigative work in order to figure out what is the charge. By either there's a long method where you write it all out, and I'll show you that, or you can reverse swap and drop, which works like 95% of the time. You'll just have to check your work from there. So when we're looking at our transition metals, these are everything in groups 3 through 12. So I'm just going to kind of hold this up. And with your groups 3 through 12, we already wrote down that you have your Roman numerals there. However, there's two elements that don't live in the transition metals, groups 3 through 12, but we treat them like they're transition metals. Those two elements are tin and lead. Tin and lead can have a different number of electrons depending on how it's bonding. So with tin and lead, they're going to get Roman numerals just like all of your transition metals, even though they don't live with the transition metals themselves. So groups 3 through 12, tin and lead are all going to get Roman numerals for your cation charge. So as we're looking at these, you're going to, in order, like I said, to write the formula, you're going to use the Roman numeral for your charge because you can't look it up, and you swap and drop. If you're writing the name, you're going to have to figure out what is that Roman numeral, which you can tell from the formula itself. So in order to do these examples, I have my document camera here and a periodic table. I'm actually going to do the bottom portion first because those are easier, and then I'll jump up here to the top when we have to write the name. So in order to do these with your name and you have to write the formula, we have to swap and drop. It's kind of easier in a way because the charge of the cation is given. This chromium 3 means that I have chromium with a +3 charge. Now my Telluride is Tellurum. It's IDE, so I know it's on the periodic table. For my Telluride, I'm going to have to look that one up. So when I look this one up, Tellurum is here. When it becomes Telluride, it has a -2 charge. So we would have Te -2. Once we have the plus and the minus, they go away. The 3 drops over here, the 2 drops over here, so you have Cr2Te3. Same thing, I have molybdenum, Vi is 6. So you have Mo plus 6. Sulfide is sulfur on the periodic table. Sulfur on the periodic table has a -2 charge. So with that -2 charge, let me get lights back. Those really didn't want to turn on, sorry. So sulfur has that -2, so you have S -2. So again, my plus and my minus are going to disappear. The 2 and the 6 are going to swap, so you have MO2S6. I have a 2 and a 6. Those can get simplified down. So 2 divided by 2 is 1. 6 divided by 2 is 3. So you have MOS3. On this one, I have cobalt 2. So cobalt has a +2 charge. Cyanide, if I tried to find that one on the periodic table, it's not there. because it's a polyatomic ion. There's 2 polyatomic ions that end in IDE, cyanide and hydroxide. So for my cyanide here, I would have to look it up on my polyatomic ion chart. And when I look up cyanide on my polyatomic ion chart, it's Cn with a -1 charge. Again, my plus and my minus disappear. The 2 travels over here, so you end up with CO and then Cn2. So with this one, or any of these, you just use the charge that's given, look up the other charge, and then swap and drop. Now on these, we have to write the name. When we write the name of them, I have to give the charge that was used to swap and drop, because that would kind of disappear if I just had chromium telluride. I wouldn't know what they used to actually make that formula. So with these, you're going to have to do some investigative work. When you do that work, usually what I try first, I just reverse the swap and drop. When I reverse the swap and drop, I always do the anion first just to check it to make sure that it works. So this 3 would come back over here to phosphate. That would be -3 because the anion's always negative. This 2 comes back over here to be +2. So all that I need to do to make sure that this is zinc 2 phosphate is I need to check the charge of phosphate to make sure that that is actually correct. So phosphate on my list is PO4 with a -3. Hey, I got -3. That one worked. So when I go to name this, Zn is zinc. Zinc has a +2 charge. PO4 is called phosphate. So this one is called zinc 2 phosphate because they used a +2 charge to swap and drop for my zinc. Zinc's always +2, so you could have known that too. Don't tell anybody. No, really, make your life easier. On this one, I have a ghost 1 right there. So that 1 comes back over here to chlorine to be -1. If I check that on the periodic table, chlorine is a halogen. It has a -1. So this one is going to work. 3 comes back over here to be +3. So on this one I have iron. There's a +3 charge that they use, so iron 3, and then chlorine is chloride. Now on this last one, SnO. Sn is tin. Tin is not a transition metal, but we treat it like one, so it's going to get Roman numerals. And then O is oxide. To figure out what goes in the Roman numerals here, I'm going to try to reverse my swap and drop. Right now I have a ghost 1 and a ghost 1. So the 1 comes over here to be -1. I'm going to check that on the periodic table. Oxygen on the periodic table always has a -2. This one didn't work. So that means that this one got simplified or reduced down in order to write my final formula. So what you need to do with this, when that doesn't work, because it's not -1, you always know the charge of your anion because it's on the periodic table or it's a polyatomic ion. We just looked it up that oxygen has a -2 charge. If oxygen is -2, that means tin has to be +2 to equal 0 because remember they always cancel each other out. So that means when they went to write this out, it was tin 2 oxide because tin has a +2 charge. Now another example, I'm going to kind of move this down. If you have something like PbO2, so again I'm using oxygen just to make our life a little bit easier, there'd be a 1 that would come over here to be -1. We just looked it up that that cannot be. Oxygen is actually -2 on the periodic table. So when you go to figure this one out, I have 1 lead, I have 2 oxygens. Each oxygen has a -2 charge. So that means that my total negative charge is -4, which means that lead has to be +4. So when I go to name this compound, it would be lead 4 IV oxide. So sometimes you're going to have to do the work like this in order to figure it out with your answers. I'm trying to think of another example. This one I'm totally making up, and I don't think that this exists. It's, yeah, completely made up. I don't think this is real. But I'm using it for an example on purpose. So we have Fe is iron. I know that it's going to get Roman numerals because it is a transition metal. And then S is sulfide. In order to figure this one out, no, this one works. I'm going to still write this out the long way, just so you can see what happens. So let's say that it didn't work. I didn't pick a very good example. I'm pulling it off the cuff here. But you have sulfur with a -2. In order to figure out the charge of 1 iron, I'm going to have to divide that up. So I'm going to have +1 and +1 here. So you actually have each iron with a +1. So you have iron 1 sulfide. Because that's what they used to swap and drop in this fictitious compound here. But like I said, sometimes you have to kind of work backwards and divide it between those two. I just wanted to show you kind of an example, kind of the opposite of this one, where you have to figure it out. So you have some practice problems to work on with these. If you have questions, ask. Otherwise, in the next video, we're going to take ionic, both with transition metals and representative, and you're going to see them all mixed up.